which is different, of course, from climate. Whereas weather can change over a matter of just a few minutes and many times over one day, right? Climate is weather patterns over a long period of time. Liam, just put it right here in the trash can. So the keywords there are atmosphere, condition, and one other word. What's the other key word in that definition? Go ahead, you're not following directions.
I just got you.
Okay, put that down, get your notes up. Thank you. Keyword about weather is the atmosphere, conditions of the atmosphere, and specific time. That's the other key there. At a given specific time. For example, if I'm talking about, this is just a hot area. It's just hot. Is that weather? Or is that climate? That's climate. So is this climate? It's stormy. No, that's happening right now. Rainy could be climate, that it rains a lot. So climate is about extended periods of time over years. Over years. All right. A reminder of why we have weather. We have weather because of one word, global wind, right? We have weather because of global wind. And we have wind because of this. We have wind because we are not a marble. The earth is not a smooth marble earth. And because of that, it heats unevenly. And that uneven heating creates wind patterns, and wind patterns make weather. I'll repeat that again. Because that we are not a smooth marble, the surface of the earth heats unevenly, which creates global wind, and the winds create weather. So in all of that slide, you can just write down weather due to uneven heating of the earth and winds created. And the winds are what make us have weather. And why does all of the weather in the United States mostly come from the west to the east? Is that just because that's the way it always is everywhere? Mm-mm. Why, Betty? Mm-mm. Yes and no. Yes, the way the Earth orbits has an indirect effect of that. Lincoln?
Is it because we're actually in the equator?
Okay. Mm-hmm. But where we are in the Earth makes a difference.
We have mountains on the east and west. Maybe that affects like the wind.
Okay. Also good guess. It's because of the wind patterns in the Pacific Ocean. Because the wind patterns of the Pacific Ocean are going to blow all the weather, all the fronts are literally being blown from our west. So they're actually moving off the Pacific Ocean into the United States because of the wind patterns in the Pacific Ocean. So remember, the wind patterns are permanent. They blow certain directions in certain ways all the time, just because of the topography of the Earth, the way it's valleys and hills and mountains, and because of the fact it spins on its axis at 23.5 degrees. Yep. So, Jayla, is there a way to try to refresh that? See if that will come back on or not. Probably not. All right, it's fine. All right, there are six things weather includes. You do need to write these 6 down. Notice the 6th one has 2 parts. And all of these things are measured. All of these things are measured. Maybe not with a tool, but with observation. So these are the 6 areas. If I were to ask you on a quiz, what are the 6 areas weather includes? You would say temperature, clouds, sun, humidity, precipitation, and wind. And wind, we're talking about the direction of the wind and the speed. Why does it matter, the direction and speed? Well, of course it matters, because the direction can change what your precipitation or what your weather would be like. If you're having a southerly wind or northerly wind, those make a difference. And of course the speed makes a difference too, because a calm wind or a light wind tells you probably fair weather. But Natalia, if the wind speed is really high, what does that indicate probably? Not guarantee, but it probably means we have approaching front, right? Some active weather approaching. Not a guarantee, but probably. All right. How do we measure air temperature? How do we measure air temperature? Samara, how do we measure air temperature? What tool? Thermometer, right? Thermometer. How do we measure cloud cover? Observation. Not a tool. Observation, right? How do we measure sunlight? Observation, right? How do we measure relative humidity? How do we measure relative humidity? Yes. A psychrometer. Psychrometer. Starts with a P, but sounds like an S. Psychrometer, because the P is silent. Psychrometer measures humidity, and it's known as the relative humidity. The relative humidity. There is also wind speed and direction. There are 2 tools that we use there. Fred, what's one of the tools? Anemometer. Okay. Does it do direction or speed? Direction or speed? Yep, you're right. Measures wind speed. And a wind vane measures the direction. A wind vane is literally you just have something spinning on a post, and the way it spins tells you the direction the wind is blowing, right? So if you're looking at a wind vane and it's spinning, do you call it the direction it's spinning from or the direction it's spinning toward? All right. There's one more thing that we do talk about in weather, and that is pressure, barometric pressure. Say again? Oh, I'll get there. Thank you. That's good. So if you'll add also down here, pressure, barometric pressure, and we measure that with a barometer. So a 7th item to add on there. These are the things that you could observe and see, including you could observe relative humidity. You might not be able to observe the barometric pressure, but you would know what the barometric pressure is causing. Because if the barometric pressure is falling from higher to lower versus rising, that means fair weather or active weather. And jot this down. If the pressure is falling, that's active weather. If the pressure is rising, that's fair weather. So the 7th thing to add on there is pressure, barometric pressure. Again, if it's falling, that means active weather. If it's rising, that means fair weather. And remember, by active and fair, I mean precipitation is active weather, not precipitation is fair weather. And do high pressure and low pressure have anything to do with temperature? No. That word high and low there is not referring to how hot or cold it is. It's about the air pressure. Is it high air pressure or low air pressure? And low air pressure goes up or down. High air pressure goes up or down. Low, high, right? But if you have air masses and they're converging and the pressure is coming down or falling, that means it's a front that's why it's active weather, because it means it's a front that's coming through of low pressure and it's making the pressure go down, right? That's why falling pressure means active weather. Does that make sense? Because it means that front is actually lowering the air pressure, because that's the kind of front that would bring in precipitation. And as Lincoln said, we didn't say precipitation, and obviously we measure precipitation with a rain gauge, or what else? Two things. Rain gauge or ruler. A ruler? How? Yeah, if it's not liquid precipitation, we measure it with a ruler. Like if it's hail, we measure its diameter with a ruler. If it's snow, we measure how deep it is with a ruler. If it's liquid, we measure it in a rain gauge, which has a ruler on the side of it. Yes.
Can't you like just have the water in a cup and just turn it in?
Yep. That's just a homemade rain gauge. Yep. So here's your thing. So if I just have a puddle, can I go measure the puddle and say how much it rained? That's very unreliable because you don't know how much the puddle absorbed. So, but could a bucket sitting on a step or a cup? Yeah, if you're sure it was clear before it was empty before it started and was not, not under the eave of the house, those kinds of things, or a tree, then that would give you a pretty decent accurate measure. But you don't want it to have something over it that would not let the full amount of precipitation fall in. Yep.
Wouldn't it affect it if there are different areas? Because I have driven through that. I have driven through snow and rain where it'll be coming down really hard, and all of a sudden we'll get to a certain point in a road, like we'll be in the mountains or something, and it'll like immediately go
So,
really high.
what you're getting at is, if I just have one rain gauge and say that's what it rained here, how do we know that's what it rained everywhere? We don't. It's only as accurate as how many rain gauges you have. Because the question is, can it rain more here and less right over there? Yes.
Would it affect, like, what if you put it right in between that spot, where it goes from light to heavy?
That's still going to be a different amount.
It's more of like a
Because let's say this was the heaviest, this was the lightest, where it went in between is going to be a different measure than either one of those. So the truth of it is, when you see how much it's rained, you're just knowing that's approximate because that's what it rained exactly in that one spot. And if it's like a pop-up in the summertime, it could pour at your house and just a mile down the road it hasn't rained a drop, right? Or you can literally be, there could be patchy precipitation and you don't get any and then somebody else gets a lot. So it depends on where the rain gauge is.
Because my dad, at his high school, he had gone out with work, and there was right in between, like right almost in the center of the parking lot, where it was like drizzling and then it was heavy rain.
Yeah.
Like that. But
Which is why I grew up on a farm, and everybody who worked on a farm that had a farm, you had a rain gauge, because the weather report might say we've gotten this much rain, but that doesn't mean you've gotten it there at your farm. So you were actually keeping track of how much is raining at your house to know about if you need to irrigate crops, because that rain gauge is going to be different all around because of the amount of rain. And let's say it rained everywhere, it didn't rain necessarily exactly the same amount either. That's exactly very possible. Yes.
I have an example of that. When I was at home, it was like storming, and then we went to Smyrna, and then it
Was it?
stopped.
Yep. You drive in and out of it when you go through. That's exactly right, Ashley.
I was driving with my mom one time on the interstate to the zoo, and it was like you could see like a line in the sky,
Yeah.
like it was raining, and then like as soon as I crossed
You
the
can
line-
literally see it coming at you. You can see you driving away from it. You can see it because either two things, you're moving, but it's probably also moving. I mean, it is moving, but it may be moving. You may say it's not moving, it's sitting still. Well, it is moving just really, really slowly. But a lot of times it's moving so quickly you can see it, but also you're driving, so it's both things are moving. Lincoln and then Betty.
The separation from the rain and dryness, like can have like lighter rain sometimes. So one time when we were driving, then it was like light, really dark and peaceful. Right at that line, light and shut exactly.
Yeah, it can be unnerving. And you all know how you know if a storm, how fast a storm is moving, right? You listen for the thunder, right? Or you look for the lightning. Which one first? Lightning, then count till you hear the thunder. Lightning, count till you hear the thunder again. And if you count further, it's moving away. If it's less, it's coming toward you. So you count it once, you count it again, and if you counted more numbers, then that means it's going away from you. If you count less numbers, it's coming toward you. And again, you want to do it more than like twice, but that's how you know. So you look for the light, you listen for the thunder, you look for the light and you listen for the thunder. Look for the light and you listen for the thunder. Here's why. You look for the lightning because lightning travels at the speed of light. Sound travels at the speed of sound. Remember this. Lightning travels at the speed of light. That's 186,000 miles per second. 186,000 miles a second. Okay? Sound is about 780 miles an hour. So 186,000 miles a second versus hour. 700 something. Right? Less than 1,000. So light is way faster than sound. So that's why you see the lightning before you hear the thunder. Yes?
So what that means when you're talking is like you make the motions of your mouth and doing something. I mean, like,
Yes, except that's still so fast that that's going to be instantaneous. But I have a perfect story of when I was a kid and where I grew up. Somebody was getting some concrete poured somewhere down the road, and as the cement mixer guy was coming, he took the curb and somehow rolled the cement mixer over and had a wreck. And so they came and cut the stuff apart, and they just rolled the actual cement mixer thing over, and it wound up permanently living in a ditch on our farm. But they had cut it open. So think about a kid. It was a perfect place to play because here's what it was. So here's the big cement mixer thing. There's about half full of cement in it that, of course, dries. And they've cut a circle out into the container so we could just walk in there and we could fight and play and bring the cats in there and the dogs. It was like a little clubhouse out in the middle of a pasture, except it was kind of covered around by trees. But here's the thing. When they were working on the wreck, we were sitting at our house, and so my parents have a real long driveway, and then from the porch you can see down our driveway and around down the road. And so where it happened, we were watching them, and you could see the guy hitting, like they were hammering on it, and you could see him hitting, and you'd hear the noise as he was doing it back. So the noise wasn't hitting our ear as the motion of the hammer was. It was delayed effect. So that was when I remember, because I was like first, second grade, I was like, why is that happening? And I remember whoever the adult was with the zoo, my nanny, explained what was going on. So I still remember that when you said it. But you could literally, if you're far away from something, you can see the motion faster than you could hear the sound. But that's why you see the lightning long before sometimes you hear the thunder. But they're still both really fast. It's just light is a lot faster traveling than any sound would ever be. Yes, Kimani.
I was gonna use something else to answer Lincoln's question.
Okay.
Is partly how that happens is also it happens like if you're super close, like you the what you see and the noise is almost in sync because you're so close. But also if you're further away, I forgot.
If you can see something really far in the distance and you can hear it because it's so loud, it might not be exactly with the motion because you can see further. You can see something far enough away that an instant can happen before the sound gets to you by traveling that 700 and something miles an hour. Okay, Ashley.
Is that what happens like when you like an echo? Like me and my friend who were like yelling our names, we were like calling out our names, and like 5 seconds later, finding their names like that.
Well, that's because sound waves are being bounced off of some kind of container that's echoing you. So it's in something is bouncing the sound off. Is what's making that happen. But it is still the fact that it's not instantaneously like light is. For example, when you look at the sun, which you don't without protective gear, but when the sun's out in the sky, you're seeing the sun, and that light from the sun occurred 8 minutes before we're seeing it, because we're 93 million miles away from the sun. And so traveling at 186,000 miles a second, it would take 8 minutes if you left the sun going at the speed of light, it would take you 8 minutes to get here. So that's called 8 light minutes. So that we are from the sun 8 light minutes. And I'm going to really quickly explain what a light year is. A light year is about 6 trillion miles. It's the amount of distance that light would travel in exactly 1 year, 365 days. So it has nothing. So a light year is not a measure of time; it's a measure of distance. Instead of saying this really, really long amount of miles, that's a bigger unit of measure of length. So somebody decided, well, let's say that a light year is the speed of light times 1 year, and then that's that 6 trillion thing that I mentioned. Okay, so the nearest star to us is about 4.5 light years away, so it'd be 24, 25 trillion miles away, which in space is not that far compared, relatively speaking, to everything else. But in our little solar system, we could talk about distance from the sun in light minutes because it's a lot closer. We also call the distance from the Earth to the sun an astronomical unit. You remember hearing that last year?
Yeah.
Okay, so an astronomical unit we decided as another measure to say the distance from the Earth to the sun is an AU. And then Mars is about 5 AUs. And Jupiter is about, Mars, let me get this straight. Okay, I'm forgetting now. Pluto's about 40 AUs away. Neptune, so Uranus, Neptune, so 40, 30, 20, 10, 5. So there are basically that many. So that many sun to Earths times that many. Okay, so that's just a real quick reminder that light is a really fast thing, but in the bigger picture of space, it's really not a big thing. Okay, yep.
I was gonna say, you know how like you say something, the sound goes outward like that, and as it goes outward, it goes down.
Because it's a sound wave, it goes out like a wave.
So is it possible that you would technically hear what everyone in the entire world is saying at the same time, it's just so faint that your brain cannot process it?
Yes and no. The sound waves are absorbed, and so they would only get so far because they've absorbed with the environment surrounding around them. Right? Think about if you soundproof a room, what are you doing, Kimani? If you soundproof a room, you're putting up a material that absorbs sound, right? You all notice those maroon things in the cafeteria between the windows? Those are sound absorbers.
No.
To make the cafeteria, the volume not be as loud, because when we first built the building, when the building was first built, those weren't there, it was much louder in there until they got them installed. But that's what those are there for. So that's why, Kimani, if there were nothing to absorb it, then the answer to that would be yes. But there are things that absorb the sound wave, right? Does that make sense? Just like light is absorbed. Melis,
So if the sun explodes, or when the sun explodes,
we'd be 8 minutes seeing it.
okay.
Yeah. Fred.
You said that Pluto was 40 AUs away.
Uh-huh.
Does that mean that if we had some way to look at Earth from Pluto, then we'd be looking 5 hours before anything happened?
So it'd be about.
5 hours before.
So in other words, if you take 8 minutes times 40, that's how long. It's not that many hours. It's not hours, but if you took 8 minutes times 40, well, yeah, it'd be several hours. So the sunlight on Pluto would be several hours old before they saw it. Yes. Just do 40 times 8 minutes. That's correct. Okay, Kimani.
If that's true, how do we know that like most of the stars in the sky have already exploded? They're just too far
You
away
don't know
for us
that.
to notice.
No, that's right. You don't know that. Because you're looking at, for example, if I'm looking at Alpha Centauri, that's the closest star to us, it could have exploded a year and a half ago, and I won't know it for another year and a half, 2 years, 3.5 years. So 3 years. No.
No.
Let's say that stars have a switch, and they can turn on and off, and they went blink, 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 blink. It'd be 4.5 years before we ever saw that blink, 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 because it's that far for light to get to us.
I was half paying attention, so I heard the closest star.
Well, there you go. Got to listen all the way.
Sun?
Yeah.
Yeah, you were half listening. That's right. The closest star besides the sun is Alpha Centauri, and it's 4.5 light years away. So if they blink their light, it'd be 4.5 years before we would see that blink. If the sun blinks, it'd be 8 minutes and we'd see that. Okay, last three things. Last three things. You're interrupting. Yes.
So
Hang on before we go any further. Reminder to 2 or 3 people, remember, don't interrupt, wait your turn. Okay? No side talking. Thank you.
okay, so if a UFO crash landed on Mars, we wouldn't see it for another hour or a couple hours.
We would see it in close to an hour. But here's the thing. It would have to be really big for us to even see it, because even the size of Mars is just looks like a little stardust at night.
You see like a little.
Because it's called relative size. It's what it looks like to us from where we are. That's called relative size. Yes. Okay, I said not talking. Waiting your turn.
I was gonna ask, how do we know that our nearest star, not the sun, is super big and super far away, like big enough that we could see it as a normal star, and if we look at it through a telescope or something, it's in a certain shape in a way that it would look like it's close.
So what's the question now?
What?
Say that. What's
What
the
if it
question?
exploded, but we won't see it till like eons and eons later? It's just that. Right?
That's possible. It's not about the big. It's about the far away.
I know. I said
So,
I don't like what
No, what you're saying is right. It would have to be really, 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 really enormous for us to even be able to see if it's really, really far away. Because let's say it's the size of Alpha Centauri, which isn't super big, we wouldn't be able to see it because it would be so far away we couldn't even see it.
No, but it's just that big.
But if it's so big that we could even still see it in the night sky, but it's that far away, it'd have to be really, really big. And it could be gone out and died for many, many years before we ever quit seeing its light in the sky. That's correct. So in what you're looking at, scientists say that when you're looking in the night sky, you're looking into history because everything you're seeing is already happened.
I have another question.
Because we're just getting the light to us. Go ahead.
Nelson's question said if the sun exploded, we wouldn't see it for 8 minutes. When we do see it explode, would it just disappear, or would it see the explosion?
I'm sure you could look that up.
So you would just
Okay, Musketeers, quit interrupting. You're the ones interrupting. Every one of you, stop. So, I'm sure you could look that up, and an astrophysicist could give you like some details of what we might see. You would be blinded by it. I know that, so you wouldn't really see anything because you'd die. But if you were able to withstand all that, I'm sure you would see lots of vivid colors from the explosion, but it would kill you. So let's move on from that. Okay, Ashley.
I have two things. One, what do you mean it takes 8 minutes for us to see the sun when you look up at it?
So light travels because light is a wave, just like a sound wave. But light's different because light travels is like a wave, but it also behaves like a particle. So particles, but it also travels like sound waves. Because you know what it means to, like if I throw a pebble in the water and it wakes, the waves ripple out, right? Sound does the same thing. Light travels the same way. So what I'm saying is light travels 186,000 miles a second. Well, 93 million miles traveling at 186,000 miles a second, it would take you 8 minutes to go that distance. So the light traveling that, even at the speed of light, it's 8 minutes before we'd see the change.
I thought you meant like when you look at the sun, you have to wait 8 minutes to see.
No, what you're seeing, if you're looking at the sunlight, that's 8 minutes old.
And also,
That specific light that's traveling out.
And also, wouldn't we like?
Okay, really, last three things. Don't anybody else raise your hand because I would love to, but we got to finish. Put your hands down. Okay, Betty, then you, and then you. Go.
Okay, so you're saying that, well, so like if like the sun exploded,
Uh-huh.
so like you said we would see the sunlight that's 8 minutes, that's like 8 minutes old. So
We wouldn't see that change for 8 minutes because it would take it that long for us to see that change.
So like if we could actually see the sun as a ball like in the sky, we would like see it over to like 8 minutes after. Wouldn't we be dead by then? Yeah, we
Yes. Yes, you wouldn't live through it, but if you could, it would be 8 minutes before you saw it. But you wouldn't survive because that's the energy that supplies the whole universe. That's the gravitational pull that keeps us in the spinning in the solar system. Right?
We go and we crash.
Okay, so how fast does sight travel?
Light.
No, sight.
So that's light.
You mean how fast?
So here's the thing: light hits your eyes, and then they interpret that into those shapes. They're interpreting. So the light is reflecting and refracting on your eyeballs. Yes. Last thing.
We were talking just now Pluto right now. It was like 5 hours and 20 minutes.
Whatever 8 times 40.
But will we be seeing if we were at Pluto, we could see Earth. Will we be seeing 5 hours in the future or 5 hours in the past?
Past.
Because if it was the
It's already happened.
because if it was
From
in
the
the
past.
future, the light wouldn't even exist yet.
Right.
Yeah.
It's from the past. All right. Quickly. Thermometer measured. You don't have to write this down. You already know it. Thermometer measures temperature. We have 2 temperature scales we use. In the United States, we use Fahrenheit. But most of the rest of the world uses Celsius. And what I do want you to remember is on the Fahrenheit scale, which is what's called a customary measure. You might want to write that down. Fahrenheit scale is customary. Customary means it's the thing that we started using and we continue to accept as the thing to use. If we say it is customary that Dr. Underwood gets on the announcement, says the mission, does the pledge, does the moment of silence, right? And that's just the custom of the way we start the day. Fahrenheit is a customary measure. Just like inches and feet and miles and cups and ounces and all those are customary measures. They're the measures that our society in the Western world started using centuries ago and still use. All of the metric measures are all newer measures that were created to simulate the customary measures, but in base 10. So everything's in 0 to 9, right? So it all is in tens or hundreds or thousands or whatever. So in our United States, we still, for most purposes, use all customary measures, which means in feet, we're in base 12. In yards, we're in base 3. In clocks, we're in base 60. And on it goes. Ounces to pounds, we're in base 16. So we do all these fractional amounts. But that's what we've learned and used, and I don't see it changing. When I was younger than you, they kept saying by the year 1970 or something that we would all we'd convert over. It never happened. It's not going to happen. But Europe does. There's a girl in 8th grade who was in 6th grade 2 years ago, and we were doing weather. Her family is from Canada. Her relatives are in Canada, so when they go there, she could always tell me how to remember about what this temperature would be in Celsius, because that's what they do. But the thing you do want to remember is, in the Fahrenheit scale, water freezes at 32 degrees. Water boils at 212. I've already told you this earlier this year. In the Celsius scale, that same distance, instead of going from 32 to 212, which is 180 steps, so that's like 180 steps. So if I'm saying I'm going from here to that TV, and I'm going to do it in 3 steps. 1, 2, 3, okay? If I'm doing that same distance in granny steps, there's a lot more of them, right? A whole lot more of them. Now, these dozens of steps, did I go any further? No. I measured the same distance with little small things versus those big things. So that's all I'm saying about this. Fahrenheit is measuring from boiling back to freezing in 180 degrees. Celsius does this in 100 steps. So they say, we're going to make water freezing 0, water boiling 100. So if it were 100 degrees Celsius, we'd die. The most it's been on the earth would be like 50-something Celsius, if that. But if they say outside it is 1 degrees in Celsius, you're like, that's okay, because that's like 33, 34, right? If they say outside it is -5 Celsius, you're like, okay, I can do that. That's probably in the teens. But -5 in Fahrenheit is below 0 for what we think of with temperature. So that's what I'm saying. So you have to watch when you're looking at stuff. If you have a weather app, you can tell it to be on metric Celsius or on Fahrenheit. You can tell it that. And it's kind of fun to go in your settings and change it and look at what the temperature would be. But just to quickly say, I forgot what I was going to say about it. Oh, I know what I was going to say. So on your paper, the study guide, where you had to fill in those lines in the box about freezing rain, hail, sleet, snow, and it said at or above the 0, 32, they were giving the Celsius and the Fahrenheit, right? So it's freezing or below freezing. So if you were doing that for Celsius, that would be a 0. If you're doing that for Fahrenheit, that's a 32. All right. Couple things I want you to take away from here about the Earth's atmosphere. We are studying weather, which is the behavior in the lowest part of the atmosphere, the troposphere. So we're watching behavior in the troposphere. And it is mostly made up of these things. You do need to jot this down. Is because we haven't talked about the atmosphere. We'll do a little activity on the atmosphere later. But here's what you need to take away from that. Our atmosphere, the higher up in the atmosphere you go, the more dense or less dense? Less dense, right? Right. because you're on the bottom of it. Think of the atmosphere as a bunch of blankets on you. And if you've got 20 blankets on you under that, that's heavier than if I'm on top of the blankets. All right? So the atmosphere is more dense at the Earth's surface than it would be up in the atmosphere. That's why if you go up on Mount Everest, the oxygen levels are less because there's not living trees up there to do the carbon dioxide oxygen cycle. So you have less oxygen. It's also less dense, but the oxygen is less because there's the lack of things to create the oxygen called living plants, right? Producers. Nitrogen, carbon dioxide, and oxygen. Writing this down. Put that away, please. Because that's distracting. And remember that over 80% of that is nitrogen. Oxygen of the atmosphere is like 5-8%. Yep.
We actually, pure oxygen isn't good for us. It can make us sick. So that's why we need a lot of oxygen.
Pure oxygen would also be very dangerous because it's extremely flammable. Yes, it's explosive.
So
Pure oxygen, one little spark would make an explosion. That's why if you're in a hospital, there are rules about, because they have oxygen tanks being used, and you have to be super, there's protocols because it could make an explosion. All right, so quick reminder here. This is going to be important for later. Reminding those same people to stop and look and listen. Cold air contracts and sinks. Okay? Cold air contracts, sinks. Hot air expands and rises. Here's an example. This ring is tight in the summer. In the winter, it's loose. When my hand's cold, it's loose. When my hand's hot, it's tight. Because literally, this finger and this ring in heat expand, and in cold they contract. Right? So another story from the farm, when we would have to put up a fence, you always wanted to put your fence up in the summer or the winter? Summer or the winter? The answer is summer. Can anybody tell me why? Why would you want to put the fence up in summer? Because it's not cold? No. Well, that too. But there's a scientific reason. And my dad taught me this, and I still remember it. Because when you're putting up a barbed wire fence, you go from one post to the next one, and you actually have this thing, and you crank it to pull it really tight. And then you get the steeple that's like a nail that's like the shape of a U, and you put it right behind a barb, and you nail it in, and then the barb holds on there and holds it tight. Why do you do that in the summer? Imani?
you do it in the summer so that it's easier to do because when you pull it tight, also the cold will pull it down, and also.
So when you pull it tight in the summer, it's the metal has contracted, or has it expanded?
Also, I have another question.
Wait, is it contracted or expanded? Expanded in the summer. So then in the winter, when it contracts, it's just going to stay tight. Now, if I pull that really super tight in the winter, and in the summer it expands a little bit, it's going to sag a little bit, right? So you want to do that in the summer when it's already expanded, so that it stays tight. Yes.
The reason that California pulls the wires hanging out a little bit is because in the winter, if it was straight in the summer, or in the winter they would.
Yep. That's why there's a natural hang to the wires, because of contraction and expansion. So I don't know if you've ever noticed, but if you look at a big building or even your house, there are gaps in the brick. That's for expansion and contraction. So if you ever look at big brick walls or big brick buildings, ever so often there'll be like a solid line all the way down. Because on the bricks, it's every other one, they're staggered. And you'll get to a spot where there's no overlap, and it's just a big long line down through there. That's a filler that's got rubber in it so that it can expand and contract. That's not concrete. So there's literally a gap in the bricks every so often to allow for contraction and expansion, especially the expansion in the summer, because they actually expand. So warm air expands, and then that makes it rise because it's less dense, right? Because what are the molecules doing when it warms up? They are literally expanding, and that makes them less. James, I know you don't know all this, right? Give me your attention. And if they pull apart, they're less dense, they rise. Okay, so I'm going to have everybody to focus back in, and let me say that again because half of you didn't take it in by the fact you weren't trying hard enough. Say it again. When air is heated, it expands and rises. It literally expands because the molecules inside are further apart. And the molecules being further apart make it less dense, right? If I've got a bowl that's got 6 Skittles in it, I can do this. If the bowl is full, it's going to be harder to move it around. They'll fall out and everything. Okay? More dense. When air cools, the molecules come together, they contract, more dense, it sinks. That's the reason it happens. Why this is important right now is because all of our weather is because the earth heats up unevenly. So when things expand or contract, they rise and they fall, and that rising and falling is what makes weather fronts, and that's how we have weather. Because that makes wind, and the wind, all the weather just travels along those wind paths. And plus more than that. Okay, yeah.
So you know how you said, like, when you put a cup outside in the summer, it, like, forms the water around it, and, like, but in the winter,
It condenses on the outside of the cup if it's cold. So you set a cup of iced tea outside, and it starts sweating all around the outside. It gets wet. The cup gets wet, right?
Yeah,
Makes a ring on the table
in the winter and summer.
in the summer.
I did that when I got home, and it was like a cold day. It was this winter right now, and it still formed that ring.
So was it out there a long time?
Yeah.
That's why. Because it will eventually melt some because the ice was colder than the air temperature outside. But it will happen really quickly in the summer. And sometimes it won't happen because you'll have it drunk in the winter before it would ever do it, right? But in the summer, it starts getting wet outside pretty quickly because 2 things. It's cooling at a much faster rate because it's trying to warm up to the air temperature, and the air temperature is trying to cool to it, right? And there's a lot more moisture in the air in the summer than there is in the winter. And that's literally the water in the air, the humidity. Yes?
If you put super hot air inside like a balloon, does it like expand more hot?
It would if you put enough.
And then if you know like dry, the air that comes off it, like if you get like super cold air, put in that balloon, would it like shrink?
Yes, it would. Yeah. Because the fun with science people used to come and do that. Make it shrink all up. It does, that's right. Because all the membrane of the balloon just contracts down. And if you take it out of the big dry ice thing, it will go and go big again. Yeah. And if you do it really fast, it will pop. But if you do it slowly, it will shrink down, and then if you let it out slowly, it will just get big and go all the way back again. But if you don't do it slowly, it pops it. Yes, sometimes it still pops it.
So hot air expands. That means that if you put like ice up to the brim in a cup, it'll go back down once it melts.
Yes. Yep. And all that ice in your cup is taking up space from the volume of your cup, right? Yeah. But if all that ice melts, would you have the same exact? Here's my question. So let's say you fill your cup at McDonald's with as much ice as you can get, and then you put the Dr. Pepper on, and go all the way to the top, and then you just very carefully go sit it on the table and go off, and come back. Nobody bothered it, and the ice is all melted. Will it still be exactly at the top?
No.
It'll be less because that ice being frozen was taking up a little more space than when it melted, volume wise. Yes.
That, yeah, volume wise, but like I like to drink ice water, so I've set it down like to go watch TV, and then like I'll come back and like the ice is melted and like there'll be more water in it because the ice is melted and added to the water.
So it will water it down because that ice is melted and the volume's in there. But like, let's say your drink, the ice was sticking out at the top, and you let it all the way melt, then it would go all the way up and maybe go out of the cup because you had some of your volume actually more than your cup because it was sticking out in frozen form, right? So I think that's what you're talking about. Is that right? Is that what you mean?
Like fill it up to the top?
Yeah.
I didn't do that.
Didn't. Okay.
So you said the hot air expands and rises. So if you heat up a man, would
Heat up what?
if you heated up a person hot enough, could the person
Okay, moving on. No.
If you put a hot
All right,
gas on
it would not. All right, notice this graphic right here. Did you need?
no, I'm good. Thank you.
So on the graphic, what are you noticing? Are you needing the?
I'm so sorry. Comcast.
Yeah.
Box.
I've got a picture of it. Can I send you the picture?
I just need the serial number this time.
Okay.
I thought I had. I'm so sorry.
Okay. Can I send it to you after?
Yeah.
Okay. All right. So the circulation. What do you notice about the circulation? And what do you notice about the geography? Clockwise. That's correct. Clockwise. What else do you notice? Yes.
So the hot air is pushed towards the clouds, and then when it comes down, it gets cooler.
Mm-hmm.
And then because of the shape of the mountain and the water, it pushes back up and heats up again, and then just keeps going.
And it makes a convection. And that's the reason we have weather, because of the geography. So it's got to have the geography, we got to have the gravity, all of that together is why we have weather like we have. Yes. Hey, last thing, because I've got it, because we're way behind.
Wind is higher up in the air, higher up in the atmosphere, the wind blows harder, and also, it's snow, like, whenever precipitation comes like clouds, it's snow at first, but how would that, like, would the heated air be the thing that we did for the, precipitation?
Yes, but that's way up higher than this,
Oh,
where that's happening. That's way up higher than this.
didn't know those.
Right. The clouds are not drawn to scale correctly there. Yeah, they'd be higher than that. Yeah, good that you're asking that question. But they would be higher. They wouldn't be that low. All right, there's another example of what convection literally looks like over a candle. As the air goes up, it's warm, and then it cools as it goes out. It falls because it becomes more dense, right? And then it heats back up and goes up, and then it cools and falls, and it circulates, right? All right, I think we're going to stop there. Let's just do this real quickly. So wind, we've already said this, I think. It's simply the air that moves in our atmosphere caused by the uneven heating of the Earth's surface. Oh, this. And it's always going to move from high to low. And that should make sense because it's going to fall. Right? High pressure is going to move to low pressure. The air is going to move in that direction like we showed a minute ago with that clockwise position. And this makes sense, right? That if you have an extremely low pressure system, so let me say that again, I didn't just repeat the same thing. If you have an extremely low pressure system, so the L on the weather map, if it has circulation around it that's really, really low, that's when you would have tornadic or severe weather, because that's going to be the biggest difference with the higher pressure, and they're going to try to do what? Quickly balance, right? And that quick balancing is going to create all that energy, and that's when you could have a tornado. So strongest wind and possible tornadic activity would be around a low pressure that is extremely low. And if you have a tornado, it's going to be around an L on a map. If you have a hurricane, those hurricanes always start as an L in the ocean. And then all of the moisture of the ocean feeds into it and makes it get bigger and bigger and stronger and stronger. And that's why hurricanes form. And they only form at a certain time of the year because that's when the water is at its warmest, and that's what makes them happen. There are lows happening in the Atlantic Ocean all year long, but they're not as likely to get strengthened to the strength where the winds will make it a hurricane, because the water is not usually as warm as it would be in the summer. That's why hurricane season is like June to November, because that's when the water is at its warmest in the Atlantic, where they form. They form off of Africa and come west. Yeah, west. All right, so that's where we'll stop with that. Okay, you go ahead and pull out your Ed puzzle, because we never got to that today. It's about 10 minutes, and then you'll have PLT to finish up whatever you need to do after that. Okay, so the Ed puzzle is literacy. So if you go ahead and get that out, do that first. Again, go to your Ed puzzle app. You have the